Hi everybody, welcome to this section 1.1 video for our Math 240 course, Differential Equations. This is the first video of many lecture videos. So let's go ahead and get started on our first content. So this section is titled Definitions and Terminology. And that's mainly what we're going to be doing in this section, defining some key definitions of differential equations. So our learning objectives for this section are going to be define differential equation through type, order, and linearity. We're going to verify and understand solutions of differential equations. And then we're going to just identify intervals of solutions to some differential equations. So that's our section in three parts. Okay, some of this stuff looks familiar that you probably covered in calculus too. But let's go ahead and recover that again today. So let's define what is a differential equation. So an equation containing derivatives of one or more dependent variables with respect to one or more independent variables is what a differential equation is. Okay, so if we look at some examples down below, here's a derivative, here's a derivative, and y prime is also a derivative. Okay, so something you probably learned in calculus 2, or you should have learned. If not, it's okay. That's what this class was for. But let's go ahead and expand upon this. And we need to classify differential equations according to some type, order, and linearity. Okay, so let's go ahead and look at types of differential equations. So let me go ahead and label this one, and I'll say this is one. Okay, so if a differential equation contains only ordinary derivatives of one or more unknown functions with respect to a single independent variable, it is said to be an ordinary differential equation, essentially ODE. Okay? We don't like to say ordinary differential equation. It's a mouthful, so we just say ODE. So down below, we just have a couple examples of a ODE. Um, because we just have a single independent variable. So what does that mean? Let's look at this dx right here. dy over dx. That's a derivative of y with respect to x. Okay? Just a single independent variable. Let's look at example B. We have d squared y over dx squared minus dy over dx plus xy equals 0. So this is also an ODE because all the derivatives of y are just with respect to x. So that's the independent variable, x. All our derivatives are with respect to a single independent variable, x. So same thing with example C. We have dx over dt, dy over dt equals 2x plus y. Yeah, it's dx and it's dy, but it's all with respect to dt. Okay, so that's why it is a ODE. Everything is with respect to the single independent variable. I'm going to erase this x, but here I'll say like with respect to t. Okay, so let's keep moving. Let's go ahead and define what a partial differential equation is. So an equation involving partial derivatives with one or more unknown functions of two or more independent variables is called a partial differential equation, also known as a PDE. And that's when you have derivatives with respect to more than one variable. So if you look at example A, it's d squared u dx squared plus d squared u over d squared y equals 0. This is more than one independent variables. Okay, we have two independent variables. Okay. And if you look at example B, we have, again, two independent variables. It'll be X and T. And same thing be for C, two independent, oops, excuse me, X and Y. Okay, we have a bunch of independent variables going on. So that's what makes it a partial differential equation. More than one independent variables, meaning like derivative with respect to. Okay, so let's keep moving through notation. And this one's just about like how we like to write differential equations and the derivatives are written inside the equation. So there's really one way that you've seen before, like Leibniz notation, and that's just like the, dy over dx, right? This guy right here. Um, you might prefer that, you might not. The one thing about it is that it's easier to see the independent and dependent variables. So here you would know that the independent is x and the dependent is y. Uh, but that's mainly the positive of Leibniz notation. Otherwise, it's prime notation, just y prime, y double prime, y triple prime could be like x prime, x double prime, x triple prime, so on and so forth. But that's just notation of differential equation. Okay, so last thing for uh last couple things before we finish up this video is talking about order and linearity. So the order of a differential equation is the order of the highest derivative in the equation. So this is something that you probably came across in calculus 2 maybe. But order is just whatever the highest derivative is. So in this example, we have d squared y over dx squared plus 5 times dy over dx cubed minus 4y equals e to the x. Okay, so order is just the highest derivative. And what would that be? That would just be 2 because d squared is just the highest derivative. Don't be confused by this dy over dx cubed. That's not the derivative. That's just saying the derivative is cubed. So be careful with that. So here I'll say like not uh, third derivative, just cubed. Okay, so that's example A. Let's move on to example B. dy over dx plus 5y equals e to the x. What do we think the order is? Take a second, see if you can figure it out. But here the order would just be 1, and it's dy over dx, just a first derivative. Okay, so let's finish this out. Let's talk about linearity, the last thing we need to cover. Sorry, I forgot to label them. Linearity, and notation, right? Type, order, and linearity. So to finish up this problem, we're going to define what linearity and non-linear is. Linearity is just a DE that satisfies the following properties. The coefficient functions must only be in x, y, and the derivatives are only to the power of 1. So let's look at the standard form of a DE, a sub 2x, y double prime plus a sub 1x, y prime plus a naught of x times y equals g of x. And so the key here is that our a sub n's are functions of x only, and we call them coefficient functions. Okay. So nonlinear is just a differential equation that's not linear, doesn't meet the the linear properties. Okay. That's pretty much it. You know, so let's go ahead and look at an example of linear and nonlinear. So if we look at example two, got a couple of questions here, a couple of differential equations. We want to see which ones are linear or not. So question one, we have y double prime minus 2y plus y. Uh, let's see, the coefficients must only be in x, y and the derivatives are only to the power of 1. Okay, this looks to me like it is linear. Okay, question two is d to the fourth y over dx to the fourth plus y squared equals 0. This to me would be non-linear. Okay, we have this y squared here because what's the issue? Is that y and its derivatives are only to the power of 1. So we have a y squared there, which makes it nonlinear. Okay, so what I want you guys to do is pause the video and try out examples 3, 4, and 5. See if you can determine linear or nonlinear. Okay, welcome back. So hopefully you tried these out. And for example 3, this is going to be nonlinear because what happens if I distribute in this y prime? This would be y prime minus y prime plus 2y equals e to the x. But the issue here is that our coefficient terms needs to be in terms of x. That's one of the properties of a linear, is that the coefficient functions must be only in x. Okay, so that causes an issue here because it is in terms of y. So this would be non-linear. And then we'll just keep going. We'll just say like question four is linear. Okay, no issues there. All our coefficients are in terms of x. Y and its derivatives are not raised to a power. And then same thing with question five. Okay, so hopefully you got these right. If not, double check what happened and understand what went wrong. But that's it for this video. I'll see you in the next one. Okay, bye.